Suppose we have a parametric curve in R2, and that we want to find the signed area of the slice formed by going out from the origin to the points at t equals a and t equals b. To do this, let us consider an infinitesimal change dA in the area over an infinitesimal change dt in time. Since dt is infinitesimal, dA is essentially the area of this triangle, which is half the area of the parallelogram formed by the vector with coordinates x of t, y of t, and this other vector, which can be obtained by adding the little vector along the infinitesimal changes dx and dy in the x and y coordinates to the first vector. Since the parallelogram is formed by these vectors, we can get its area by computing the determinant of a matrix whose columns are those vectors, which gives us this result after some manipulations. Integrating this over the desired values of t gives us the desired formula for the area of the parametric slice. Let us consider a circle of radius r centered at the origin. If we cut through the leftmost point of the circle to some other point on the circumference of our choosing, and let t denote the y-coordinate of the point at which the resulting chord cuts through the y-axis, then we can exploit the similarity between this triangle and this triangle, where the scaling factor from the smaller to the larger is 2r squared over r squared plus t squared, to conclude that we can parameterize the circle using these equations. We will use this parametrization in the formula we just derived to find the area of the circle. Now, it's a little bit annoying, but straightforward to get that the derivatives of x and y turn out to be this, where at least the negative sign in the switched x and y can be explained by the fact that a tangent vector to a circle is perpendicular to the corresponding radius. This fact can be shown using implicit differentiation. Next, we want to figure out which values of t to integrate over. But since it's impossible to actually get to the leftmost point of the circle using this parametrization, we're going to want to get around that by letting the lower bound approach negative infinity and the upper bound approach positive infinity. Now we can just throw everything into the formula to get this. We can simplify further by factoring out r squared from the numerator and the denominator, making the substitution u equals t over r, and pulling out constants, leaving us with this simple integral. We recognize this integral to be pi, and at this point you might be tempted to verify this using the fact that the integrand is the derivative of arctangent, but what I am going to do is to define this integral to be pi. But wait, if this is how we're going to define pi, how do we recover the equivalent definition of pi as being the ratio of the circumference to the diameter? Well, all you have to do is apply the formula for the arc length, and there you have it.